All right, so our third skill in this learning unit on kinetics should be a little bit more straightforward because hopefully what you're going to see is it's a little bit of a review and a variation on the theme, because we're going to be talking about integrated rate laws and then chemical kinetics. Okay, so let's remember what a rate law tells us, right? Rate law, this is what we learned about in our last skill here, tells us how fast a reaction is proceeding at the moment when you have a certain concentration of reactant A mixing with a certain concentration of reactant B. You can solve this reaction for rate. So we can answer questions like what the concentration of B is when A is a certain concentration. But one of the things that you'll see here is that there's no variable of time in a rate law. So we can't have a rate law tell us how long will it take to use up a certain amount of A, or what the concentration of A will be after a certain amount of time. So hopefully you remember that when we were doing stuff with our nuclear chemistry, we had an equation that had 4 variables, and that's sort of what we're getting at here, an integrated rate law. So the magic of calculus, and I'm not going to get into the details, but for those of you who are a little bit interested, remember we had a rate expression that said rate equals change in concentration over change in time. And then we had a rate law, rate equals rate constant times the concentration of reactants raised to powers, right? If we set those two rates equal to one another and we have this magic of calculus, we basically can get to what's called an integrated rate law. Integrated rate laws have 4 variables: the amount that we start with, the amount that we have left, the amount of time that has passed, and the rate constant. Right? If we look at our last learning unit on first order decay processes, this is a slide from that. We had a first order rate equation that, again, to tell us the amount of reactant that we start with, the amount of that species that we have after some time has passed, the amount of time that has passed, and again, the rate constant that we have. Okay, so we've seen this before. So this really is just a variation on the theme. That was a first order reaction. We now know that there's second order processes, maybe even 0 order processes. So it just expands the number of equations that we have. Okay, I'm not going to go through the details of sort of explaining this, but you do need to know and recognize the equations that are different. Here's the first order reaction. Okay, first order reaction, first order rate law looks like this. This is the one with the ln in it. You will be given these equations, but I don't tell you which one is which. The first order process is the one that has the ln with it. Second order process and second order integrated rate law looks like this. Okay, we're going to have 1 over things. Second order rate law would look like this. Okay, you need to recognize that this is a second order equation. Notice that it has the same things: how much you start with, how much you have after a certain amount of time, and how much time has passed, but a different flavor of the equation. Here's the same 4 variables in an equation for a 0 order process. Okay, you need to be able to recognize which one of those equations you're going to need to use. We also have corresponding different equations for second and 0 order processes for half-life. Remember this equation for half-life? It allows us to interconvert the half-life and the rate constant for a first order process. We've got a similar kind of an equation for a second order process, and then for a 0 order process. Again, ways to help you remember this is sort of the ln flavor of an equation. This is the 1 over flavor for a second order process, and this has a sub-0 kind of in the numerator here. You do need to remember which ones of those are. This is going to be how this information is given to you. Just a laundry list of equations. You need to pick out the one that you need. All right. So again, how do we do these problems? You first need to pick the correct integrated rate law. The easiest way is that the problem is going to tell you, in this first order process, this second order process, this 0 order process, you still need to match and use the right equations, but maybe the problem directly tells you if it's first, second, or third order. A little bit harder is, well, maybe you're given the rate law and then you'll need to use the exponents to infer the order of the reaction and then pick the right equation. I'll talk about this on the next slide. You can look at graphical data to tell you whether or not it's a first, second, or zero order process. The hardest, and you are not going to see this in class here, but this is related to things that happen in lab, is maybe you'll need to use experimental data, that method of initial rates, to determine your reaction order. Well, once you choose the correct integrated rate law, or know that the rate law is what you have, know what the order of the reaction is, then you're going to choose the equation that you're going to need, right? You can use the half-life equation. Here's your half-life equations. You might need to use that half-life equation to solve for K, and then solve for the desired variable. How much did you start with? How much do you have now? How much time until, or how much time has passed, right? Some time piece of information. A little bit on this graphing piece, it sort of relates to these equations that we've seen. When you have a linear relationship, when you plot the ln, that tells us that it's a first order process. When you have a linear reaction, when you plot 1 over, that tells us that it's a second order process. And if there's a direct relationship between reactant concentration of time and time, that tells us it's a zero order. Okay, so maybe it's a graphical piece of information. You might see a qualitative piece on your quiz that asks you what the order of the reaction is when you see this plot, right? And you have to kind of correlate that. All right, so let's do one practice problem, and then this skills video is done. So we've got a 1000 degrees C reaction here where we're having cyclobutane decomposing in a first order process. So again, they tell us right here that it's a first order reaction. They actually give us the rate constant, so we don't need to do anything with half-life here. They actually give us the rate constant. And so they're asking two pieces of information here. So let's go through and work through these independently. They tell us the initial concentration, right? The initial concentration is 2 molar. We want to know what is the concentration after 0.010 seconds has passed. Okay, so pretty straightforward. We need to choose the first order rate law equation. So ln of, and again, we're going to have the amount that we start with. And sometimes you'll see this written as a sub 0 and a sub t for amount, okay, equals kt. Okay, we're going to put in the pieces that we have here. So ln of, we've got 2, and I'm just going to put that in as 2 over a sub t equals 87 seconds to the minus 1. And then we're going to multiply that by 0.01 seconds. So remember, an important thing is making sure that we've got units that match here, right? If for some reason we had either the rate constant given not in units of reciprocal seconds, or if this was in minutes or something like that, then we need to do a little bit of unit conversion to get everybody into the right units, okay? This is going to be equal to 0.87, okay? 0.87 reciprocal seconds. Remember, we can take e to get rid of what's on the left-hand side there. So now we're going to have 2 over a sub t is going to be equal to 2.4. So the amount that I have left after 0.01 seconds has passed is 0.83, and my units were moles per liter. Okay, so remember, this is not surprising. This is a pretty fast rate constant. So even though a tiny amount of time has passed, we actually have gotten rid of a lot of it. So this is the amount that's remaining. Okay, I'm going to insert another kind of slide here so we can answer our next question. So again, we answered this question. What's the concentration that we have? This is the amount that we have after 0.01 seconds have passed. Now we want to know, what is the fraction that has decomposed? Okay, so I'm going to come over here and kind of highlight a few things. Remember, when you hear the word fraction, we always want to think part over whole. Okay, so part over whole, okay, the whole is how much we started with. So the question is what do we have in our numerator here, right? If we want to know the fraction that is remaining, we think the fraction that's remaining, That's going to be our A sub t. That's what we solved for in part A. But that's not what it's asking, right? It's not asking the fraction remaining. It's asking the fraction that was decomposed. So that's, said another way, that's the fraction that has reacted. That's what we want. To figure out what's reacted, we need to take what we started with and subtract what's left. And this will give us the amount that's reacted. Okay? So if we take the 2 that we started out with, subtract the 0.83 that's remaining, okay, that's going to give us the amount that we have that has reacted. So again, putting this in as it asks for fraction, so it's going to be A sub 0 minus A sub t over A sub 0. So again, that's 2 minus 0.83 over 2, and that equals 0.58. If it had asked for it as a percent, it would be 58%. Okay, so hopefully, even though this is kind of a new skill, I hope that you see that it's a lot of the same flavors that we saw when we did nuclear decay first order processes. We just have 2 new sets of equations to think about, whether they are 0 order or second order processes.